we're going to tackle a beast of a topic, Apache Kafka. But we're going to do it through the lens of a system design interview, building it up from first principles so you can really understand what makes it tick.
So, let me ask you a question. How do the biggest companies on the planet, we're talking 80% of the Fortune 100, deal with just an insane amount of data? I mean, trillions of events every single day. Well, for a lot of them, the answer is Apache Kafka. But instead of just giving you a dry list of features, we're going to do something way more fun. We're going to invent it ourselves, starting with a really simple example.
So let's set the scene. Imagine you and I are running a website that gives people live, real-time updates for the World Cup. You know, every goal, every yellow card, every substitution, it has to show up on the site instantly. This one scenario is going to be our guide for figuring out exactly why Kafka is built the way it is.
Okay, so at first, things are pretty simple. We've got a producer, maybe a reporter typing in updates, sending those updates to one server. Then we have a consumer that reads from that server and puts the updates on our website. Easy enough. But what happens when our little website gets wildly popular? Like, imagine the World Cup expands to 1,000 teams, all playing at once. Yeah, our single server is just gonna melt. The obvious fix, right? We gotta scale out. We need to add more servers to share the load. But adding more servers creates a huge new problem. Ordering. If we're just spraying events randomly across all our new servers, we completely lose any sense of time. You could see a message about a goal in the 80th minute before you see the substitution that happened in the 75th minute. That's no good. So we need a smarter way to distribute these events. And the solution is to make sure that all the events for one specific game, say Brazil versus Argentina, always go to the exact same server. That way, for any single game, everything is guaranteed to be in the right order.
Okay, so we fixed ordering, but we've really just moved the bottleneck. Now our poor, lonely consumer is trying to drink from like 10 different fire hoses at once. It just can't keep up. The natural thought is, hey, let's just add more consumers. But if we do that, we could have 3 different consumers all grab the same goal, event, and display it 3 times on the website. Yikes. The trick here is to group them into what's called a consumer group. This is a clever way to guarantee that any single event is only ever processed by one consumer in that group. No more duplicates.
All right, one last challenge. Our website is a huge success, and now the boss wants to add basketball updates too. But we can't have a LeBron James slam dunk showing up on the World Cup feed, right? We need a way to keep these different streams of data completely separate, and this is where the idea of topics comes into play. We can create a soccer topic and a basketball topic. Producers send their data to the right topic, and consumers can choose to listen only to the topics they care about.
And, believe it or not, that's it. Without even knowing the fancy terminology, we just walked through every major problem and designed the fundamental architecture of Apache Kafka. Scaling, ordering, consuming, organizing, we figured it all out.
So, using our World Cup site, we basically just invented Kafka from scratch. Pretty cool, right? Now, let's just make it official and learn the real Kafka terminology for all the pieces we just put together.
First up, remember those servers we added to handle more traffic? In Kafka land, each one of those is called a broker. It's really just a server in the Kafka cluster. Its main job is to hold on to the data. Simple as that.
And what about the queues that those brokers were holding?
Kafka calls these partitions. Now, a partition is a super important concept. It's an ordered, unchangeable sequence of messages. The best way to think about it is like a log file on your computer. You can only ever add new lines to the end. And because it's so simple, writing to it is incredibly fast. Plus, a single broker can handle tons of these partitions at once.
Okay, this is a super common point of confusion, so let's clear it up right now. The difference between a topic and a partition. A topic is just a logical name, a category you decide on in your code, like soccer events. A partition is the real deal. It's the physical file on a broker's hard drive where that data actually lives. One topic can be split into many, many partitions, and that's the whole secret to how Kafka scales. So just remember this, topics are for organization, partitions are for scale.
Okay, so now we get the architecture. But in that system design interview, when's the right time to pull Kafka out of your tool belt? Let's talk about the main jobs it's really good at.
Kafka really plays 2 major roles. First, you can use it as a classic message queue. Think of it as a big, reliable buffer between your services. It's perfect for when you want to do work in the background or just let different parts of your system talk to each other without being tightly connected. The second role, and this is where Kafka really gets powerful, is for stream processing. This is when you're dealing with a never-ending flow of real-time data that you need to analyze or react to, like right now.
Let's make this real. For asynchronous stuff, think about uploading a video to YouTube. You don't wait for it to process. Kafka lets that happen in the background. For ordering, think of Ticketmaster's virtual queue. First come, first served. To decouple services, imagine a code submission platform taking thousands of submissions at once and grading them all separately. And for real-time aggregation, think of a dashboard counting ad clicks the second they happen. All of these are perfect fits for Kafka.
All right, you've nailed the basics in your interview. Now come the follow-up questions where you really show you know your stuff. Let's start with the biggest one. How do you actually scale this thing?
Before we even get into the weeds, there is one golden rule with Kafka: keep your messages small. The official advice is to stay under 1 megabyte. A classic rookie mistake is to try and shove a giant blob of data, like a whole video file, into a Kafka message. Please don't do that. Instead, upload that big file to something like Amazon S3 and then just put the URL of the file in the Kafka message. This keeps your cluster zippy and happy.
Listen up, because this is probably the most important thing I'll say about scaling. Your choice of a partition key, that little piece of data we use to decide which server a message goes to, like our game ID from earlier, is everything. A bad key creates what's called a hot partition, where one poor server gets hammered with all the traffic while the others just sit around doing nothing. A good key spreads the love evenly.
So what happens when you do get a hot partition? Well, you've got 3 main escape hatches. Option 1, if you don't care about the order of messages, just get rid of the key entirely and let Kafka distribute things randomly. Option 2, and this is the most common fix, is to create a compound key. If a super popular ad is causing a hotspot, you can just stick a random number on the end of the ad's ID. That'll spread the messages for that one hotkey across multiple partitions. And option 3 is basically to just tell the producer to chill out for a second and slow down. We call that back pressure.
Okay, next deep dive topic. The classic engineering headache of durability versus performance. How do you make sure you don't lose data without slowing everything down to a crawl? Let's look at the trade-offs.
Kafka stays durable by making copies of your data. This is called replication. There are 2 settings you absolutely have to know. Replication factor is easy. It's just how many copies of your data you want to have. More copies means it's safer, but you'll need more disk space. Then there's AX. This controls how many of those copies have to write back and say, "Yep, got it," before your producer can move on. If you set AX to all, you get maximum safety, but it's going to be slower because you're waiting on a bunch of servers to reply.
What about when things go wrong on the consumer side? Well, Kafka keeps track of how far a consumer has read using something called an offset. Every now and then, the consumer tells Kafka, "Hey, I've successfully processed all messages up to this point." That's called committing the offset. And here is the critical part. You must commit that offset only after your work is successfully finished. If you commit it first, and then your consumer crashes, well, Kafka thinks the job was done, and that message is gone forever. You've just lost data.
Now here's a funny thing about Kafka. It doesn't actually have a built-in retry system for consumers. So the community came up with a standard pattern. If a consumer fails to process a message, it doesn't just die. It sends that message over to a special retry topic. A different consumer can pick it up from there and try again. If it still fails after a few tries, we finally move it to a dead letter queue, or a DLQ, where a human engineer can step in and figure out what went wrong.
And finally, let's talk about how to make this thing fly. It's all about maximizing throughput. From the producer's side, you have some really powerful knobs to turn. The first is batching. Instead of sending messages one by one, which is super chatty on the network, the producer can group them together into bigger batches. It's way more efficient. Second, you can compress those batches using something like gzip. Smaller data means less to send over the network and less to store. And to bring it all home, it once again comes back to partitioning. A great partition key is the best performance tool you have because it ensures you're using your whole cluster to its maximum potential.
So at the end of the day, Kafka gives you this incredible power to scale your system, to guarantee ordering, and to protect your data. But none of that power comes for free. It is a system built entirely on powerful trade-offs. The real question you have to answer is, for the problem you're trying to solve, what balance of complexity, performance, and safety are you willing to make? I really hope this explainer helps you answer that question in your next design session. Thanks for watching.
ご覧いただきありがとうございます。